when we are dealing with the different gas mixture, okay, so then we will have to see that how we will get the state properties of these type of mixture. Okay, so this is so some topic we will take from chapter 13. Okay, so and then some topic we will take from chapter number 15. The chapter number 15 is related to the chemical reaction. So the chemical reaction, I am talking about the combustion reactions which are taking place inside your combustion chambers in the automobiles or either in the type of power plants. Okay, so we will see that, but this is just a basic overview. We will not go into more detail that related to the chemistry part. Chemical is not also the course outline in the course outline. Okay, so we will just see and we will cover this chapter 13 and 15 in hardly 2 or 3 lectures. Okay, so now coming to the introduction. Okay, so far the thermodynamics system involving a single pure substance such as water and homogeneous mixture of several pure substances like air, which we have already studied in the previous chapter, which is chapter number 9 and chapter number 10. So now, unlike air, it is a non-reacting gas mixture. So we define air as a non-reacting gas mixture. In some applications, we have the reacting component also. Okay, so like in combustion. Okay, so the analysis of reacting mixture. Okay, so a mixture whose chemical composition changes during a process would be studied in this lecture. Okay, and you already know when we are dealing with the non-reacting mixture, which is air. Okay, so the type of energy which we have to take into account is the internal energy, sensible internal energy, which is associated with the temperature and pressure changes, and then latent internal energy, which is associated with the phase changes. Okay, so now when dealing with the reacting system, the chemical internal energy associated with the chemical bonds also need to be considered. Okay, so this is the main difference when we are talking about the reacting and non-reacting mixtures. Okay, so these two mixtures we commonly see in the combustion process as well. Okay, so now coming to is non-reacting gas mixture. Okay, so which is related to the combustion process. So non-reacting mixture gas mixture can be treated as a pure substance since it is usually homogeneous mixture of different gases. So if you can see that when we are talking about the burning of the fuel, so it consists not only consists of only one type of gas. There are several gases which make that type of fuel. For example, we use a gasoline. Okay, so there are different gases which make these type of fuels. The property of gas mixture depend upon property of individual gas. Okay, so whatever the gas inside it. Okay, so for example, if we need to find the internal energy of some gas mixture, so we have to add all the internal energies, which is based on the components which make that type of gas mixture. Okay, and on the amount of each gas in the mixture. Okay, so generally speaking, it is possible to prepare a table properties for mixture, and this has been done for common mixtures such as air. Okay, so if we already know that for air we have the table properties available for the thermodynamic analysis. So this is also one type of mixture because air is the combination of you already know that is a mixture of different gases. So there will be oxygen, there will be nitrogen, there will be argon, there will be neon also. Okay, so these all gases collectively make air. But it is not practical to prepare property table for every conceivable mixture composition. Okay, so there are different compositions, so it is not possible that we can develop all the thermodynamic table. Okay, so for all type of mixture, for example, if we are burning of LPG type of gasoline, okay, in your combustion chamber. Okay, so then it is not possible that we have to develop for the LPG also, then we have to develop for CNG also. Okay, so that's why we have to know that how to develop these type of properties so that we can analyze the combustion process. So therefore, there is a need to develop rule for determining the mixture properties from knowledge of mixture composition and the properties of individual components. Okay, so first rule for ideal gas mixture will be follow through ideal gas mixture. Okay, so we will see that what are these type of rules. Okay, so from which we can find the composition of gas mixture and different properties. Okay, so from the chemistry point of view, so you already know whenever we are talking about different substances in the chemical way, we define different thing which is mass and mole. Okay, so mass we can say that it is the mass that is occupied by a different substance, and mole is basically the unit by which we can represent that how many molecules, how many atoms, and how many different type of things which make one composition. Okay, so that is basically the unit in order to define the different items and percentage, which we can define as a mole fractions. Okay, so we will see that how to find these type of mole fraction and mass fraction in this lecture also. Okay, so determining the properties of the mixture, knowledge of two things is required. So composition of the mixture. So definitely whenever we have to find out some mass fraction and mole fraction, we know we have to know that what are the composition of that mixture. So that mixture is the combination of what type of substances. The amount of each gas in the mixture. Okay, so definitely we know. Okay, so now composition of the mixture can be described by two ways. One is the molar analysis. Okay, so by specifying the number of mole of each component. Okay, and then this is the gravimetric analysis by specifying the mass of each component. Okay, so these two type of analysis we usually use whenever we have to analyze the compositions. Elaborate the concept of mass and molar fraction. Consider a gas mixture composed of k components. Okay, so for example, we can say that there is a mixture. Okay, so which consists of H2 and O2, and that contains 6 kg of hydrogen and 32 kg of O2. Okay, and when we have to add, it will become 38 kg of your product. Okay, so we can say that your mixture, which is equal to mass of your mixture is equal to mass of all the components which compose that mixture. Okay, so for example, hydrogen and oxygen is making that mixture, so we have to add both of these masses, which make the total mass of the mixture. Okay, so similarly, for the mole fraction, okay, so for mole number of the mixture, which we have to denote with the NM, is the sum of the mole number of the individual components. Okay, so similar thing with the mass fraction, mass of the mixture, we have to consider for the mass of each component. So here for the mole number, we have to consider the mole of each element. So for example, the H2 consists of 3 kilomole and O2 consists of 1 kilomole. So collectively, we can say it is equal to 4 kilomole. Okay, so from here we can find the mole number of the mixture as well. Okay, so now the mass fraction. Mass fraction is basically the ratio of your mass of the individual component. So for example, we are talking about we have to find the mass fraction of hydrogen. Okay, in this reaction. Okay, so what we have to do is we have to just take the H2 mass over there and divide with the mixture mass, which is H2 plus O2 mass. Okay, so then we will get the mass fraction of your total mixture, mass fraction of that specific component. Okay, so now similar thing, we have to find the mole fraction. Okay, so the ratio of the mole number of the component to the mole number of the mixture is called the mole fraction. Okay, so we can denote mole fraction with the y. Okay, so I basically denote with the mole fraction of specific component. For example, we are talking about hydrogen, we are talking about oxygen. Okay, so we can denote with the I. Okay, so Ni is the specific thing which we are talking about. For example, we are talking about H2. So we know the moles of H2 over there, it is 0.75, and the mole of the mixture is 1. Okay, so we can just divide and we will get the fraction of that specific component. Okay, so we already see that what is the mass fraction and mole fraction. Okay, so from here we can also say that whenever we have to find the mass fraction, so your mass fraction which is summation for specific component, and for K components, and we can say M Fi, which is always equal to 1. Okay, so if we add all the mass fraction of the individual component, it will be equal to 1. And similarly, if we can say for the mole fraction, so for mole fraction for the K components, I is equal to 1, and we can say Yi, which is also equal to 1. So if we add all the mole fraction, it also become equal to 1. Okay, so now there are some specific relation which we have to define. Okay, so for example, you already know that whenever we have to find the mass of the substance, okay, so from the chemistry knowledge, so we denote with the small m, and then we can we need to know the mole number, which is n. Okay, so here n is the mole number, and if we can multiply with the molar mass of that substance, okay, so which is denoted by bigger M, okay, so we get the mass of the substance. Okay, so this type of relation we can use in this type of in this lecture also, okay, to solve some problems. So now from here we can easily say that for example, we have to know the mixture properties. Okay, so we can define molar mass of the mixture is equal to mass of the mixture and number of mole of the mixture. Okay. Okay, and in the previous slide, we already know that the mass of the mixture is basically sum of the mass of individual components. Okay, so and this is your mole of the mixture. Okay, so from here, the mass of mixture, we can simply use this relation, which is n multiplied by m, which is the number of moles into molar mass, and put into this equation. Okay, so we can say that it will be equal to summation of ni, which is the number of molar mass of the individual component, okay, and your mole number of the mixture. Okay, so from here we can define one relation, or we already know that this term, which is this, we already know that this will be equal to the mole fraction. Okay, so which we already see in the previous slide as well. So we can say that it will be equal to summation of yi, which is the individual component, and m. Okay, so this is one relation from which we can find the molar mass of the mixture. Okay, so if you have any question, you can ask me. So we will practice some question also, so that you will get better understanding of it, because it is more related towards some chemical knowledge. Okay, so I hope you already have some knowledge of chemistry from your FSC or previous courses. Okay, so now here another thing which we have to define is the gas constant. Okay, so gas constant, we already know whenever we have to analyze the gas power cycle, we have to put the value of gas constant. Okay, so gas constant we can for in order to find the gas constant of the mixture. Okay, so we use Rm, which is the gas constant of the mixture, and then Ru over mass of molar mass of the mixture. Okay, so this Ru is basically the universal gas constant. Okay. Okay, and this universal gas constant value you can easily find in your thermodynamic table. Okay, so if you can go to your property table and it's table A1. So from here you will get molar mass also. Okay, so if you need to solve some question and you need the molar mass of some specific substance. Okay, so you have to check from this table A1, and this is the value which I am talking about is the gas constant. Okay, so here is that R is equal to Ru over M. Okay, so here we can define that Ru is the universal gas constant, and its value is 8.31447 kilojoule per kilomole. Okay, so this is the universal gas constant value. So you will get the value from this table. Okay, so similarly, we can also say that mass fraction of the individual component is equal to, we already know that it will be equal to mass of the individual component and your mass of the mixture. Okay, so if we can just put the value of this mi, which is n into m. Okay, so mi over nm and mass of the mixture, molar mass of the mixture. Okay, so n is the number of mole of the mixture, ni is the number of mole of individual component, m is the molar mass of the individual component, and m is the molar mass of the mixture. Okay, so from here we can also say that your mass fraction of the individual component is equal to yi, which is the mole fraction. Okay, because ni over nm is the mole fraction. Okay, and then mi over m. So if we have to find mole fraction of mass fraction of the individual component, so and if we know the value of the mole fraction, and we know the molar mass of the individual component, and we know the molar mass of the mixture, so we can easily find the mass fraction of the individual component. Okay, so these are some relations we have to note it down, and then we will try to solve one question related to these relations. Okay, so these are the relation which is given out there, which I already described in the previous slide. Okay, so you have to go through it by yourself. Okay, so which we already discussed that here we have to find the molar mass of the mixture, and we have to find the mass fraction of the mixture individual component. So this is the relation, and this is the gas constant for the mixture. And for this, we have to divide just the universal gas constant with the molar mass of the mixture. Okay, so this is the one example. Okay, so from your book. Okay, so this is example 13-1 from your chapter 13. So you have to just read the statement first. So consider a gas mixture that consists of 3 kg of O2, 5 kg of N2, 12 kg of CH4-1 figure. Okay, so this is the figures mentioned over there. So this is related to example 13-1. So what you have to determine the mass fraction of each component, the mole fraction of each component, and the average molar mass and gas constant of the mixture. So these things we have to find from using this data. So you have to note on the data, then we move towards next part. Okay, so based on the data which is available, that we have 3 kg of O2, 5 kg of N2, and 12 kg of CH4. Okay, so in the first part, what we have to do is we have to find the mass fraction of each component. Okay, so for mass fraction, we already know that the mass fraction of the individual component is equal to mass of individual component over mass of mixture. Okay, so first thing you already have the value of mass of individual component from your data. Okay, so but we have to find first the mass of the mixture. Okay, so for total mass of the mixture, which is equal to mass of O2 plus mass of N2 plus mass of CH4. Okay, because there are three substances which we are talking about. Okay, so from here, if we can all add up all these values, just 3 is the given in your question, and 5 is for N2, and 12 is for CH4. So it will get the value of 20 kg, okay, for your mass of the mixture. Okay, so if we have the mass of the mixture, we can easily find the value of the mass fraction. Okay, so mass fraction for the first component, if you are talking about 4, so we have to find all the mass fractions for the individual components. Okay, so mass of O2 is 3 kg, and your mass of mixture is 20 kg. And from here, if we can just take the ratio of these two, it will be 0.15 is the mass fraction value of O2. Similar thing, mass fraction of N2, and that turns out to be N2 value, which is given in your question, which is 5 kg, and mass of
सर आपकी तरफ से शोर आ रहा है।
जी आई थिंक मेरी लॉबी में कोई काम कर रहा है मे बी बिकॉज देयर इज अ विजिट ओके सो शोर ज़्यादा है आपको सुनाई नहीं दे रहा बिल्कुल आवाज़ के आई थिंक नाउ इट्स स्टॉप okay so now if we can just take the ratio of these two 5 120 so it will be equal to 0.25 so this is the mass fraction of your second component second substance which is N2 so similar thing you have to apply for the mass fraction of CH4. Okay, so the CH4 value is known to us from the question, which is rep kg, and the mass of the mixture is 20 kg, and it is equal to 0.60 value for the mass fraction of CH4. Okay, so this is this question for you, part number D. So you have to note it down, then we move towards the next part. And if you have any question, you can also ask me.
एक्सक्यूज मी सर
G.
सर ये आई जो पहले फार्मूले में लिखा हुआ है इसका क्या मतलब है
I
इंडिविजुअल
is just, yes, I is representing the individual component. Okay, so if your mixture consists of 10 components, okay, so it means that your individual components are composed of individual components. You have to just add all the individual components to find the mass of some specific mixture. Okay.
ओके सर
Okay, so coming towards if okay, so coming towards the second part. Okay, so second part you just have to find the mole fraction. Okay, so for mole fraction, what you have to do is you have to find the okay, so we already know that the relation which is n is equal to okay, so mole fraction is equal to y, which we already see that it is denoted by y, and n of the individual component over M mixture. So you already know that this is the relation from which we can easily find the mole fraction. Okay, so now here first we need to find the Nm, okay, which is the mole number of your mixture. Okay, so for mole number of mixture, we have to find first the mole number of individual components. Okay, so for mole number of the individual components, okay, so what you have to do is, so you already know that one relation M is equal to N M. Okay, so mass of the substance is equal to mole number and multiplied by molar mass. Okay, so from this we can easily find the mole number of the individual component first. Okay, so for example, the first is O2. Okay, so simply we say that NO2 is equal to MO2 over MO. Okay, so now MO2 value is known to you from the question. Okay, so just 3 kg. Okay, so now molar mass of O2, simply you have to go to table A1, okay, and you can easily find the value of the molar mass of your oxygen. Okay, so if you cannot remember it, okay, so you will just find it out and you will put 32 kg per kilomole. Okay, so if we can solve it, it will be equal to 0.094 kilomole of your O2. Okay, so this is the first component for which we have already find the mole number. Okay, so now similar procedure we have to adopt for the second component, which is the N2. Okay, so the mole number of N2 is equal to mass of N2 over molar mass of N2. Okay, so mass of N2 is known to us from the question, which is 5 kg, and molar mass of N2 you can easily find from table A1, which is equal to 28 kg per kilomole. Okay, so if we can just divide these two things, we will get the value of 0.179 kilomole of N2. Okay, so similar, now we have left with another thing, which is CH4. Okay, so CH4, which is mass of CH4 over molar mass of CH4. Okay, so mass of CH4 is known to us from the question, which is 12 kg, and molar mass of CH4 is equal to 60 kg per kilo. Okay, so if we can just take the ratio of these two, we will get 0.750 kilomole. Okay, so now we have all the mole numbers with us. Okay, so if we can just now we have to find the mole number of mixture. Okay, so we just have to add this these all values. Okay, so Nm is equal to NO2, mole number of nitrogen, mole number of CH4. Okay, so if we can add all these values, we will get which is equal to 1.023 kilomole. Okay, so now we have the mole number of the mixture. Okay, so from here we can easily find the mole fraction of the individual components. Okay, so you have to note it down, then we go towards the next slide. So now by using the relation which is yi is equal to ni over nm, okay, so we can easily find the mole fraction of all the individual components. Okay, so for example, we have to find the mole fraction for your O2, which is equal to mole number of NO2 and your number of mole for the mixture, which we already found in the previous slide. Okay, so mole number of oxygen from the previous slide is 0.094 kilomole, and your mole number of mixture is 1.0. Okay, and from here we can find that YO2 is equal to, with the mole fraction of the oxygen, 0.09. Okay, so this is the first component. Now the second component is N2. Okay, similar thing. So you just need the mole number of N2 and mole number of mixture. Okay, so mole number of N2 is 0.179 from the previous slide, and the mole number of mixture is 1.023. And you just have to take these the ratio of these two, and it will be equal to 0.175 of your mole fraction for N2. Similar thing, mole fraction of CH4. So mole fraction CH4 is the number of mole for individual component CH4 and your mole number of your mixture, and it will be equal to 0.750, which we already found in the previous slide, and 1.023 kilomole. And if we just take the ratio, it will be equal to 0.733 value for your mole fraction of your CH4. Okay, so this is the procedure you have to find the mole fraction of individual components. So if you have any question, you can ask, and then we'll move towards the part C. Okay, so the part number C, what we have to do is we have to find the average molar mass and gas constant of the mixture. Okay, so average molar mass or average molar mass, basically it is the meaning is that we have to find the molar mass of the mixture. Okay, so you do not have to confuse that with this the average molar mass here. Okay, so simply we can say that molar mass of the mixture is equal to mass of the mixture and number of mole of the mixture, okay, so which we already see that M is equal to capital M into molar mass. Okay. So from here we already know the mass of the mixture, okay, so which we just find in the part A, which is equal to 12 kg, 20 kg. So just we have to add all the values, okay, we will get the mass of the mixture. And similar thing, we also know the number of mole of the mixture from the part B, which is equal to 1.023. So you just have kilomole, and this is kg. Okay, so if we can just take the ratio of these two things, we will get 19.6 kg per kilomole of your molar mass of the mixture. Okay, so now the one thing which is left is okay. Another thing is you can also find the molar mass of the mixture by using another method. Okay, so if you do not have the value of mm and nm, okay, so you can just see that your molar mass of the mixture is equal to summation of yi mass fraction of the individual component and the mass molar mass of the individual component. Okay, so this relation we already seen in the previous slide as well. Okay, so simply if you can just take all the mole fraction, which is YO2 molar mass of O2 plus YN2 molar mass of N2 and plus YCH4 and MCH4. Okay, and you just add these all these three things. Okay, so you also get the molar mass of the mixture. Okay, and the answer is same, which is 19.6 kilojoule per kilogram. So you have to note it down. Then go to the next. Okay, so now the last thing which we have to find is the gas constant of the mixture. Okay, so which we already seen that the relation for the gas constant of a mixture is basically the ratio of two things, which is the universal gas constant Ru and your mass of the mixture. Okay, so Ru value you can simply go to table A1, okay, and you will get the value 8.314 kilojoule per kilomole dot Kelvin. And mass of the mixture you can get from the previous slides, which is 19.6 kilogram per kilomole. So now we have two things. We can just take the ratio and we will get the gas constant of the mixture as well. 0.424 kilojoule per kg dot Kelvin is the value for append. Okay, this is also the required thing from the question. Okay, so now the solution is completed. So if you have any question, you can ask, and then I'll move towards the next one. Okay, so now coming towards the next question. Okay. Next question is also related to the mass fraction of the mixture. Okay, so for this, what we have to do is, in this question, the composition of the moisture is given on a molar basis to be 78%, nitrogen 20%, nitrogen 78%, oxygen 20%, and H2O 2%. Okay, so these are given on the mole fraction basis. Okay, so it's mean that if you can just divide by 100, it will be equal to the number of your mole fraction. Okay, so for example, for the first part for nitrogen, we have 0.78 mole fraction. Okay. So similarly for O2, we have 0.2 mole fraction, which is the value of Y, and 0.02 for the water H2. Okay, so in this question, we have to determine the mass fraction of the individual components. Okay, so we have to note on the data and we will go to the solution. Okay, so in order to solve this question, we already see one relation from the previous slide, which is the mass fraction of the individual component is equal to mass fraction of the individual mass of the individual component and mass of the mixture. Okay, so now here we already know that N is equal to Ni Mi molar mass of the individual component. Similarly, number of mole of the mixture and molar mass of the mixture. Okay, so from here we already know that this term is equal to mole fraction. So it is Yi Mi over M. Okay, so if we have to find the mass fraction of the individual component, so just you have to multiply the mole fraction, which is Y, which is given in your question, and we need the value of molar mass of the individual component, and we have to find the value of molar mass of the mixture as well. So So this is the question, and now we have the relation also. Okay, so now we will see how to solve it. Okay, so first thing we have to find the molar mass of the mixture. Okay, so for molar mass of the mixture, I already told you that we can simply say that summation of mole fraction of the individual component into molar mass of the individual component. Okay, so from here we already know the mole fraction from the question. Okay, so for example, we know the value of N2, okay, which is the first component. So we can say that 0.78, and molar mass of the N2 is 28 from table A1. Similar thing is for the second component, which is 4. Okay, so we can say that 0.2 into 32 is the molar mass of 4, and plus 0.024 H2O. It's the mass fraction of mole fraction of the H2O, which is given in the question as well. And you just have to multiply the molar mass of the H2O, which is equal to 80. Okay, so if you have add all these values, you will get the molar mass of the mixture, which is equal to 28.6 kilogram per kilo. Okay, so now we have the M value with us. Okay, so now by using this relation, we can easily find the mass fraction of the individual. You have to note it down, then move towards the next one. Okay, so for the first thing, we need the value of mass fraction of N2. So for mass fraction of N2, we can simply say it will be equal to mole fraction of N2, which is mentioned in your question, and molar mass of N2 over molar mass of the mixture. Okay, so from here we need the value of mole fraction, so which is 0.7 from your problem statement, and Mn2, which is the mass of your molar mass of the nitrogen, which is 28, and the molar mass of the mixture is 28.6. Okay, so if you can just solve it, you will get the mass fraction of the first component, which is which is 0.764. There's a similar thing we have to apply for the second component, which is mass fraction of O2. Okay, so we can just say that Y O2, molar mass of O2 and molar mass of the mixture. You can just remember this one. Okay, so for this Y02, we already know 0.2, 32.0, and 28.6. So from here we can say that it will be equal to, we can just solve 0.224. So now we have left with one thing, which is mass fraction of H2. Have to find. So mass fraction of H2, mole fraction of H2, molar mass of H2, and molar mass of the mixture. Okay, so mole fraction of H2 is 0.02 from your question. Okay, and then molar mass 18 and of H2 and molar mass of the mixture is 28.6. So if you can solve it, it will be equal to 0.013 for the mass fraction of H2. Okay, so this is the thing which we have to find. Okay, so if you can just convert it into the percentage. Okay, so we can say that mass fraction of N is 76.4% and mass fraction of O2 is 22.4% and mass fraction of H2O is 1.3% in the mixture. Okay, so now the solution is completed. So if you have any question, you can ask. Okay, so now another question. Okay, so we have to read the statement first. Okay, so it is mentioned that a gas mixture has a following composition on mole basis. So 60% N2, 40% CO2. Determine the gravimetric analysis. Okay, so we already know the difference between the gravimetric analysis and second, which is the molar analysis. Okay, so here we are talking about the mass fractions and its molar mass and the gas function we have to find. Okay, so you have to note down the data and then put the solution. So it is mentioned you have to determine the molar analysis. So it's mean you have to find the mole fractions, okay, rather than mass fractions. So here it is gravimetric analysis. So you have to find the mass fraction of the individual components, and from there you can find the mass fraction of the mixture as well. Okay, so now from the data, so first we know that it is mentioned that your 60% of the mole of N2 and CO2 mole is 40%, okay, which is mentioned in your question. Okay, so from here we can just say that the number of mole for N2 is equal to 60 kilomole and number of mole of CO2 is equal to 40 kilomole. Okay, so you have to just assume, or you can consider that the total mixture is equal to 100 kilomole. Okay, so if you can just add these two things, it will be equal to 100 kilomole. Okay, so that you will get the fraction, which is we already said that the number of the mole of individual component is always equal to 1. Okay, or you can say it will be to 100%. Okay, so from here, first thing we have to find out in order to proceed with the mass fraction, we need to find the mass of the individual components. Okay, so mass of the individual components, so we can say that mass of individual components, which is the first component, Mn2, we can say it will be equal to number of mole of N2 into molar mass of N2. Okay, so number of mole is already given in the question, which is 60. And molar mass of N2 you can find from table A1, okay, which is 28 kilogram per kilo. And if you can multiply these two terms, which will be equal to 1680 kg. Okay, similar procedure you have to talk for the second component, which is CO2. Okay, so then CO2, which is equal to the number of mole of CO2, and you have to multiply with the molar mass of CO2. Okay, so the number of mole of CO2 is mentioned, which is 40, and volume mass of CO2 is 44 kilogram per kilo. And if you can just multiply these two terms, you will get 1760 kg. Okay, so from here we can easily find the, sorry, this is mass of CO2. Okay, so from here we can easily find the mass of mixture as well. So mass of the mixture is basically the addition of two terms, which is the individual component N2 and the mass of individual component, which is CO2. Okay, so from here, if we can just add these two, which is 1680 and 1760, we will get the total mass, which is equal to 3440 kg. Okay, so now we have the mass of the mixture with us, and we have the mass of the individual component as well. Okay, so from here we can easily find the mass fraction of the individual component. So mass fraction of the individual component is equal to mass of N2 over mass of mixture. Okay, so mass of N2 we have already found here, and mass of mixture we have already found in the previous step. Okay, so we just have to take the ratio of these two things, 1680 and 3440. Okay, so you just have to, you can just solve it, you will get 0.488, or you can say it will be equal to 48.8%. Okay, so similar thing you have to apply for the mass fraction of the second component, which is CO2, and just need MCO2 or mass of mixture. So MCO2 you have already found 1760 and 3440, the mass of the mixture. Okay, so you just have to solve it, you will get 0.512, or you can say it will be equal to 51.2% of the mass fraction of CO2 in the mixture. Okay, so now another thing which is required in this question is you have to determine the molar mass and the gas constant also. Okay, so the molar mass of the mixture and the gas constant of the mixture. So for molar mass of the mixture, what you need is you need only the mass of the mixture, okay, so which we already have with us, and you need the number of mole of the mixture. Okay, so in the initial state, we already say that the number of mole of the mixture is 100 kilomoles. Okay, so you just have to divide two terms, which is 3440, which is the mass of the mixture, and 100 kilomole. So you just get the molar mass of the mixture. So 34.4 kilogram per kilo. Okay, so here we have the molar mass of the mixture also. Okay, so you want to note it down and move towards the next part. Okay, so now the last thing which we have to find is the gas constant of the mixture. Okay, so gas constant of the mixture, you already know that we denote with the Rm, which is equal to Ru, which is the universal gas constant over um, molar mass of the mixture. Okay, so universal gas constant you can easily find from table A1, 8.314 kilojoule per kilomole per cal. And the molar mass of the mixture you have already found in the previous step, which is 34.4. Okay, so from here you can easily find the gas constant for the mixture, so which is equal to 0.242 kilojoule per kg per calorie. Okay, so this is the required thing for the this question. Okay, so now the solution is completed, and this is question 13-11 from your book. If you have any question, you can ask me, and then we'll go to the next part.
समझ लो ग्रामोमीटर लिखा होता है वो स्लाइड को, वो क्या चीज?
आज मैंने आपको पहले शुरू में बताया है कि so now whenever we have to deal with the composition of the mixture, so there are two procedures. One is the molar analysis, one is the gravimetric analysis. So gravimetric analysis is by specifying the mass of each component. So if you can notice in this question, we have find the mass fractions. Okay, we do not find the molar fraction, which is the mole fraction, which is by m. Okay, so if we have mentioned that we have to do the molar analysis, then you have to specify number of moles of each component rather than the mass of each component. Okay.
Yes.
So another question, which is example 13-3 from the chapter 13. Okay, so you have to just read the statement first. Okay, so then you will see that how to solve this type of question. Okay, so in this question, it is mentioned that insulated rigid tank is divided into two components by partition, okay, so which is shown in 13-14 figure. One component contains 7 kg of total gas at some specific temperature and pressure is mentioned over there, and the other component, the compartment contains 4 kg of nitrogen at specific temperature and pressure, which is also mentioned over there. Now the partition is removed and the two gases are allowed to mix. Okay, so what you have to find is the mixture temperature and the mixture pressure after equilibrium has been established. Okay, so these two properties you have to find for the mixture. Okay, so you have to note on the data, then you will see that how to develop the solution. Okay, so in the part number A, we have to find the mixture temperature. Okay, so for mixture temperature, so first thing is you have to apply energy balance equation. Okay, so you can say that for energy balance equation, which is energy in minus energy out is equal to change in energy of the system. Okay, so if we can just take a data system. Okay, so now here we can also, because it is an insulated compartment, so there is no energy transfer to and from the tank. Okay, so that's why we can just say that it will be equal to 0, which is over left hand side, and right hand side we can represent with the change in internal energy, because here we are not talking about any working fluid which is traveling through the pipelines. Okay, so that's why we just take as a change in internal energy rather than change in enthalpy. Okay, because whenever we are going to change in enthalpy, which we represent whenever the working fluid is moving from one component to another component. Okay, so here we can represent with change in internal energy of the two mixtures, two individual components, which is O2 and N2. Okay, so from here we can say that this is 0, and here we can say change in internal energy of N2, and we can say change in internal energy of O2, which is the two components for the tank. Okay, so now we already know that change in internal energy is equal to mCV delta T. Okay, so this relation we already know from the previous lectures as well. Whenever we have to say that change in internal energy, we can represent with delta U. Whenever there will be enthalpy, we represent with mCp delta T. Okay, so here we are talking about change in internal energy. So simply we can just put the value, which is mCv Tm, which is the mixture temperature, because once you are mixing two components, okay, so your final temperature will be equal to the mixture temperature. Okay, so because if you are mixing, for example, two liquid which is 40 and 20 degrees C, so whatever the final temperature, that will depends upon the mixing process. So Tn is the final temperature and T1 is the initial temperature of your. Okay, so here we are talking about the first substitution and so similar thing you have to apply for the second thing, which is M go to M CV. Tn is again the final temperature and T1 is the initial temperature of specific component, which is O2. Okay, this we are talking about O2. Okay, so now here we have the value of M with us from the question. Okay, so which is known to us from the question that it is 4 kg of N2, and CV value you just have to go to the thermodynamic table and you will get the value of CV easily for the nitrogen, and Tm you have to find because the main target for the part is to find the mixture temperature, and T1 is mentioned in your question that your initial temperature for the N2 is 20 degrees Celsius. Okay, a similar thing M is known to you for the O2 as well, and CV value you can easily find from thermodynamic table. Tm value you have to find, and T1 value you already have from the statement, which is 40 degrees Celsius. So you just have to plug all the values, and you will see that how what we have that for the Tm. Okay, so 4 kg for your mass of nitrogen. CV value for N2 is 0.743. Tm value we have is unknown to us, and T1 value is 20 degrees Celsius. So now here we have N for oxygen, which is 7 kg, and CV value is 0.658. So this comes from thermodynamic table. Tm value we have to find, and T1 value is 40 degrees Celsius, which is equal to 0. Okay, so if we can solve it for Tn, okay, so you just have to do some mathematical procedure, and Tn is equal to 32.2 degrees Celsius. So this is the solution for your part number A. So if you have any question, you can ask me. Then we move towards the part B. Okay, so in coming towards the part number B, so in the part number B, the required thing is we have to find the mixture pressure after equilibrium has been established. Okay, so for mixture pressure, simply because they are working on the gases, so we can say that the relation is PV is equal to nRT. Okay, so here is the R as the gas constant. Okay, for the specific gas. Okay, so now we can just rearrange this equation to form another set of equation. Okay, so from here we can say that PV, because we already know from the previous slide that M, we can say that M is equal to number of mole, okay, and molar mass. Okay, so N into molar, capital N. So now here R, which is the gas constant, we already know that your gas constant is equal to the ratio of universal gas constant to molar mass of the mixture. Okay, so this is, you can say, Rn. So here you can just put the value of R, which is universal gas constant, over molar mass of the mixture. Okay, and this is also molar mass of the mixture. This is also Nm. This is Pm. This is Vm, because we are talking about the mixture ratio. Okay, so that's why we have to develop one relation for the mixture. Then this is the Tm. Okay, so now here we can just rearrange it. We will just cancel the molar mass of mixture over there. Okay, and we will get one relation which is ratio of the mixture, volume of the mixture is equal to number of mole of the mixture, universal gas constant, and multiplied by temperature of the mixture. Okay, this relation we can use in order to find the pressure of the mixture, which is required for the part number B. Okay, so now here the issue is we do not have the value of this value we do not have, this value we do not have, we have this value from table A1, and we have this value for from previous part, which is part A. Okay, so first thing is we have to find these two values, which is Vm, volume of the mixture, and the mole, number of mole for the mixture. Okay, so for number of mole of the mixture, we need to find the number of mole of the individual component first. Okay, so for number of mole of the individual component, so there are two components, O2 and N2. Okay, so number of mole for O2 is equal to mass of O2 over molar mass of O2. Okay, so which relation we already see in the previous slides as well. So M of O2 is known to us from the question 7 kg, and molar mass of O2 is equal to 32 kg per kilogram. And if you can just take the ratio of these two things, you will get the number of mole for the O2, 0.219 kilogram. Okay, so similar thing you have to do for the second component, which is the O2. So sorry, N2. So number of mole for N2, which is equal to mass of N2 over molar mass of N2. Okay, so mass of N2 is 4 kg, just mentioned in your question, and molar mass of N2, which is equal to 28 kg per kilogram. Okay, so now you can just take the ratio of these two, you will get the 0.143 kilogram. Okay, so now we have both of these things, which is the number of mole for O2 and number of mole for N2. Okay, so now from here you can easily find the number of mole for the mixture. Number of mole of the mixture is equal to number of mole of O2 plus number of mole of N2, and you can just add these two terms, which is 0.219 and plus 0.149, and we will get the number of mole of the mixture, which is equal to 0.362 kilogram. Okay, so now we have Nm with us. Okay, so now we have to find the volume of the mixture. So you have to note it down, then go to the next one. ये वाली चीज है ना ये तो हो गया हां पीछे नहीं तो कल सुबह मेरे ऑफिशियल मतलब लेटर के हिसाब से मैंने 9:30 बजे कल विजिट है या वो परमानेंट के लिए ठीक है इसका अच्छा मेरे पास है प्रो रेक्टर सॉफ्टवेयर वो मैं कल देख रहा था क्लास आप बता रहे हैं एचओडी साहब अभी कौन आया था एचओडी से बात नहीं अभी एचओडी साहब थे डीन साहब थे और परमानेंट अच्छा बस वही थे जितना पहले हुआ था ऊपर में क्या थे वो शाह की लैब पे कंप्यूटर ऑन करने ये मैंने कहा कि था वो नहीं कह रहे यार वो ऑन कर देना शाह से पूछ के पासवर्ड क्या दे कंप्यूटर पे वो लग रहा है हां वो उस पे वो लगा वो आ जाएगा शाह सुबह नहीं आया तो वो कर देंगे हां सुबह ऑन कर देंगे ठीक हो So now coming towards the volume of the mixture. Okay, so for volume of the mixture, we can simply say that we can use the relation Pn is equal to Nm Ru Tn. Okay, so for this we can say that for example we have to find the volume of O2 first. Okay, so VO2 is equal to we just have to rearrange this equation, which is equal to N Ru and T1. Okay, so here we are talking about the temperature for the individual component. Okay, so not for the mixture. We just have to rearrange for the and pressure of the individual component, which is O2, is mentioned in the question. Okay, so the N value for your O2 is given in from the part A. Okay, we already find that is 0.219. Okay, so 0.219. Ru value you can find from the table A1, which is 8.314, and T1 value is 330 Kelvin, okay, so which is available from your problem statement, and T1 value is also mentioned, which is 100 kilopascal. Okay, so if you can just solve it, you will get the value 5.70 meter cube. So similarly, you have to find the volume for N2. So simply you need the value of number of mole for N2, which is 0.143, and you need the gas constant, so 8.314, and you need the temperature, which is mentioned in your problem statement, which is 293 Kelvin, and pressure is also mentioned in your question, which is 150 kilopascal. Okay, so if you can solve it, you will get the volume of individual component, which is 2.32 meter. Okay, so from this you can easily find the volume of mixture, which is equal to the addition of these two terms, which is 5.70 and 5.32. Okay, and you will get the volume of mixture as 8.02 meter cube. Okay, so now Vm is known to us. Okay, so simply you have to go to this equation, which is Pm, Vm, Nm, Ru, Pm. Okay, so now we have all the values. So simply we can put these values in this, and we will get the pressure of mixture. Okay, so we can rearrange it. Nm, gas constant, universal gas constant, temperature of the mixture over volume of the mixture. Okay, so number of mole of the mixture is 0.143. Okay, so which we already find in the previous slide. So Ru value is 8.314. The pressure of mixture we already find in the first part, which is 32.2 degrees Celsius. So you have to convert it into Kelvin. This is 3051.2 Kelvin, and volume of the mixture is 8.02 meter. Okay, so if you can just solve it, you will get the pressure of mixture as 114.5 kilopascal. Okay, so now this is the solution for you on part number B. Okay, so now solution is completed. So if you have any question, you can also ask me.
सर ये शुरू में U इज इक्वल टू एम सी वी डेल्टा टी, तो सर ये सी वी और सी पी कहाँ यूज करेंगे, क्या होगा तो सी वी और क्या होगा तो सी पी?
ओके, सो CV तो आपके पास जो हम पहले करते रहे प्रैक्टिस कि आपके पास अगर इंटरनल एनर्जी चेंज इंटरनल एनर्जी हम लेते हैं तो उसको हम लिखते हैं mCV डेल्टा टी. ओके, सो दिस कम फ्रॉम थर्मोडायनामिक 1. अगर डेल्टा H ले लेंगे हम उसको तो दैट विल बी इक्वल टू mCV डेल्टा T. So here we are talking about internal energy because if you can notice from the problem, there is a insulated compartment and N2 and N2 is stored inside two compartments. So there is no transfer of the working fluid from one place to another. Okay, so that's why we do not have to go for the delta H, because whenever we have to say that it will be equal to delta H, we say that working fluid is transferred from one place to another. Okay, so that's why we say that it's equal to delta H. So here we can say that it will be equal to change in internal energy. Okay, so from here we can say that Cv into delta T, and the mass is mentioned in your problem statement. Okay.
Okay, sir. Okay, sir.
Okay, so I think here we can stop now. Okay, so you just have to solve this question by yourself by changing the data. Okay, so the same question you have to solve, and you will just take the 7 as 10 kg and this 4 as 6 kg. Okay, and you just have to take the 150 as 250, and this 100 you can change it to 200 kilopascal. Okay, so these two you have to change, and then you can solve it by yourself, and you can send it to me solution.